All right, we're going to wrap up our discussion of carbon NMR. And I want to end by talking about a special type of carbon NMR called DEPT. And this is, as I said, it's a kind of unique type of NMR. It stands for distortionless enhancement by polarization transfer. You don't need to know what this means, but it's a type of carbon NMR technique that allows us to determine the number of hydrogens bonded to each carbon. But I do want to point out that in this type of carbon NMR, only carbons with hydrogens on them appear. So we don't see like carbonyls like of ketones. So if we have like, for example, acetone here, we won't see this carbon in the middle because it doesn't have any hydrogens on it. Or like a quaternary carbon. So this carbon right here in the middle, we wouldn't see that by carbon NMR because it doesn't have any hydrogens on it. So what we do is we compare a couple of spectra from DEPT with our original carbon-13 NMR. And signals will appear in one of two ways in DEPT. They'll either look like normal signals, where if this is our X and Y axis, the normal signals will go like upwards, and we call those normal or positive, or they'll appear as negative, meaning they'll go downwards. So this table kind of summarizes what we are looking for in DEPT NMR. And so in a normal carbon NMR, we see carbons with no hydrogens, as I said earlier, but we don't see them in the two types of DEPT. Don't worry about these numbers like the 90 and then that's supposed to say 135. Don't worry about what those mean. It's just two types of the DEPT NMR. CHs will appear as normal signals in both of them. However, in CH2s show up in the DEPT 135 as a negative signal. But note that they don't show up at all in the 90 version. And then CH3s do not show up at all, but show up as normal signals in 135. And that's how you can tell the difference between a CH and a CH3 is pretty much by looking, is there a signal in the 90 or is there not? And that will tell you the difference between them. So here's how a typical DEPT NMR looks, where on the bottom, we have the original spectra. Oops, sorry about that. And then we have the 135 and the 90. So notice that there aren't any signals in the 90. So what can we conclude? Well, that we don't have any CHs. Now, the way that we kind of line this up is that these signals here represent the same thing, and so on here. Now, what are these signals here that don't have any corresponding signals in either the DEPT 90 or 135? Those represent carbons with no hydrogens. So same thing with this and with this. Now, with the negative signals there, we can conclude that those are CH2s because those are the only ones that show up as negative signals in the 135. Now, since these other two signals show up in 135, but not in the 90, we can conclude that those represent CH3s. And that's going to kind of wrap it up for carbon NMR. As we transition into proton NMR, I want to highlight, um, a couple of things that we're going to notice with proton NMR. Now, as I said earlier, it's usually a little bit more complex, um, but there's just a couple of additional things that we have in proton NMR that we don't have in carbon NMR. But in proton NMR, the signals appear as peaks. So like in carbon NMR, there were just little lines, and there was really nothing underneath those lines. But in proton NMR, the signals appear as these peaks, sometimes like this, or maybe we might see two of them put together like that, or even three, or even more. But those represent one signal, one type of hydrogen. And we could do a little bit of calculus and find the area underneath those peaks. And if we compare the ratio of those areas, it helps tell us what the relative number of hydrogens are that those signals represent. This is called integration. If you've taken calculus before, you've probably calculated the integral of the area underneath underneath the curve. That's integration. And so one of the ways that we represent integration is with this kind of series of red lines. How high those lines represent, or how high those lines go, represent the integration. And all we do is, and in the old days, we would just pull out a ruler and measure the heights. So notice like this one is about 2 times the height of this one. And that's why this signal represents twice as many hydrogens as this one. And then this peak is about 3 times the height of this one. And so that's why this represents 3 times as many hydrogens. Or we could say, in contrast, this peak is about 1.5 times the height. And so that's how we can get to that ratio of 2 hydrogens to 3 hydrogens. Now, the other thing you might notice is that other than finding this integration, some of the signals are split into multiple peaks. So if you kind of look at that CH2 signal, it looks a little weird, or the CH3 looks a little weird. It's been split into multiple peaks. And hence this is called splitting, or also another term that we use is multiplicity. And with a quick calculation that we can do in our head, this tells us how many hydrogens are directly adjacent. I want you to circle, highlight, star that phrase there. This tells us how many hydrogens are directly adjacent to the hydrogen giving that signal. And I'll go through how we calculate that in a later video.